is the 5th VisDA challenge that we are hosting. And there will be more. We do not plan to stop. And therefore, if you are interested in visual domain adaptations and all kinds of visual domain adaptation for segmentation, classification, universal, rangification, the ones that we did before, please join our mailing list that you can find on our website, and you will be notified about future challenges. Moreover, after each talk, at least the live ones, there will be a short Q&A where you can ask participants and winners and speakers about the work that they presented. So there is, unless there will be more people, probably folks can just go ahead and ask their questions after the presentation. Otherwise, if there will be a lot of people, probably will use something like a raise hand function in the Zoom. There is one under the reactions tab on the bottom of the screen. After all the talks will be finished, there will be a gather town, an opportunity for everyone to speak either with each other or with challenge winners or with speakers. So check out our website that you might have probably visited already for the gather town join link and the password. So first of all, I wanted to appreciate the amount of progress that participants made, starting from the simple baseline that the OpenAD baseline that we provided. Participants made a tremendous effort to improve upon it, and they did. Thank you, every participant. That is probably, some of them are here, some of them are probably not here, most of them, but thank you everybody for pushing this task so hard. And here today we will listen for 3 presentations from 3 winners that are in red. As you probably know, as you heard from Pyotr's presentation, the ranking function that we used is the average rank across detection accuracy and classification accuracy. And these 3 participants had highest rank average rank across those 2 metrics, as you can see here. So I am personally excited to hear how they managed to achieve those amazing accuracy and detection accuracy. Okay, so the schedule that we are going to follow approximately is going to be the remarks that you're hearing right now that we will finish in a minute. Then we'll have the presentation from the 3rd place winner that is going to be recorded, unfortunately, because some participants could not make it because of the time zones and such. Then we'll have the presentation from the 2nd place winner, the 1st place, and 3 invited talks from Zhongqi about not all networks being born equal for robustness, from Xi about natural corruption robustness, and from Zhongqi Miao about challenges in deep learning. And after that, as I mentioned, we will have Gather Town. So please join to talk with speakers. Some of the speakers that we provide recordings for, they will nevertheless visit the Gather Town. So you are very welcome to join us there and to talk and to ask them questions if you have any. And that leads us to the first talk from the 3rd place winner. Let me start it in a second.
Hi everyone, I'm Haojin Liao from Beijing University of Post and Telecommunications. And these people on display are the collaborators in this challenge. Alright, and today we are going to talk about Universal Domain Adaptation of Image Classification. So, to start off, we are gonna talk about what is Universal Domain Adaptation. In real-world applications, there might be no large quantities of labeled data to train a task model, especially a deep neural network. Domain adaptation aims to learn the model from other labeled source domains that can adapt to novel target distributions. This year's Visual Domain Adaptation Challenge focuses on an open world setting. On the one hand, the input distribution is different between the source and target domains. On the other hand, the label set might be missing and also be novel classes in the target data as in the Universal Domain Adaptation setting. In this challenge, we choose overnet as the baseline method because it achieves the state-of-art performance on some public datasets for universal domain adaptation. There are three main components in overnet. The first one is the feature extractor. It can extract feature representations for both the source and target data in the shared space. The second one is a closed-set classifier that is trained on the labeled source data to learn the mappings between feature representations and known categories. And it uses cross-entropy as training loss. The last one is an open-set classifier consisting of a bunch of binary classifiers trained on both source and target data. The loss on source is produced by a positive classifier and the nearest negative one, and the loss on target is the sum of the entropy for all binary classifiers. It can help to align unknown target samples to the source samples and keep unknown instances as unknown. To improve the baseline, we first replace the backbone. Since vision transformer was proposed, transformer architecture has become more and more popular in computer vision. However, many versions of transformer need to be trained on a large-scale dataset to get good performance. According to the model size and external data requirements in this challenge, we finally choose this vision outlooker, Volo, and D3 version. Since it obtains 86.3% top 1 classification accuracy with 86 million parameters on ImageNet without other training data. Volo introduced a novel outlook attention as shown in this figure. Unlike self-attention that focuses on the global dependency modeling at a coarse level, the outlook attention encodes finer level features and contexts into tokens, which is shown to be greatly beneficial to recognition performance. However, it is largely ignored in the self-attention. Volo can be regarded as an architecture with two separate stages. The first stage consists of a stack of outlookers that generates fine-level token representations. The second stage deploys a sequence of transformer blocks to aggregate global information. The outlook attention weights are generated from the center token within the window and act on the neighbor tokens and itself. And the method is as simple as convolutional neural network using the combination of the operations, including unfold, matrix multiplication, fold, and softmax, to calculate the attention. In our method, the input of follow is same with the most Bayesian transformers, including the patches of an image, together with the class token, and the output is the feature for each patch and the predicted class. If only the class label is used as the supervised information, the detailed information of the patches will be lost, and we employ token labeling method to provide supervised information for each patch of an image. Specifically, token labeling changes the image classification problem into multiple token label classification problems and assigns each patch token with an individual label. The dense score map is leveraged to compute the cross-entropy loss between each output patch token and the corresponding aligned label in the dense score map. And the total loss is the sum of the class cross-entropy and patch cross-entropy. And this beta is a hyperparameter to balance the two terms, and it was set to 0.5. Under the Universal Domain Adaptation setting, we can get both source and target data, and the labels of source data are allowed to train the model, but the target labels are unknown. So, in our training stage, we introduced token label and class label to the closed-set classifier. It helps the backbone to extract more accurate features for known class. We also adopted a classic method, domain discriminator with gradient reversal layer. It can help to match the feature distributions of the source and target data adversarially of the known class. For the open-set classifier, we introduced multi-negative classifier loss, which is different from the baseline. When the number of categories is large, it makes the model to converge better than only one nearest negative classifier used in the baseline. And we keep open-set entropy loss the same as the baseline, which can align known target samples to source samples and keep unknown incidences as unknown. The inference stage is the same as the baseline. The domain discriminator is not used here. We first use the closed-set classifier to make a possible prediction for the target sets, and then the open-set classifier will check the unknown score of the possible prediction in the corresponding binary classifier. In this challenge, ImageNet dataset is used as the source data for training sets. The validation set is also the target domains, using images from ObjectNet, ImageNet R, ImageNet C, and ImageNet O. The test set is similar to the validation set, but with a different input distributions and category composition. The final result is evaluated by a combination of accuracy and AUC. Accuracy is only calculated on known categories, and the AUC measures unknown category detection. During our experiment, we found with the existence of the adversarial domain discriminator, the closed-set classifier can perform better on known class during training. but the open set classifier would give all samples a very low unknown score, which result in a lower AUC. To solve this problem, we introduced a two-stage training method. In the first stage, we use these four parts for training together as just described, and NMW is used as a training optimizer. In the second stage, the adversarial domain discriminator is removed, and the optimizer is changed to momentum SGD. In order to improve the unknown score quickly and maintain the high accuracy for known class at the same time, we set a lower learning rate for feature extractor and closed-set classifier, while give open-set classifier a much higher learning rate. This would finally make the model performs well in both accuracy for known class and AUC for unknown samples. In order to better understand the backbone, we used gradient-weighted class activation mapping, which is called GradCam, to produce some visual explanations for decisions from the adapted model on the validation set. As we see, for the right cases, the backbone can focus on whales correctly, but in the wrong cases, the scene in the pictures is more complicated, and the backbone might put more attention on other objects in the picture. In this wrong situation, I think humans may not be able to classify correctly, but this is a point worthy of improvement. In the experiment, we also compare the number of near-negative classifier used in open-set classifier. There is only one nearest negative classifier in the baseline, and our final proposed number is 300. As we can see, the laws of the first three figures are all convergent, but in the last one, using only one nearest negative classifier can make source negative laws of open classifier divergent. In this slide, we first show the performance of the source model VisDA-3, and then we compare different method compilations on the validation set, including data augmentation, token labeling, the number of near-negative classifier used in open-set classifier, adversarial domain discriminator, two-stage training, and 5 crops inference. The last column is the final result of our adapted model on the validation set. And here comes to the end of my presentation. I think there are still many points to improve in our methods. For example, as we just talked about, the pictures with more complex sceneries is an unsolved problem. And the two-stage training method is a little complicated. If a one-stage method can be found, it would simplify the process. And this is all my presentation. Thank you.
Okay. We would be happy to thank the presenter, but unfortunately they were not able to attend due to differences in time zones. Fortunately, we have Kuniaki Saito, who is the author of the overnet method. That is the backbone of this method. So if you have any questions about that part, you are welcome to ask them right now.
Hi, Kuniaki. I have a question.
Hi.
So with the OVA net, the it seems quite sensitive to the number of these negative samples. It seems like 1 was not enough, 300 was enough. If you continue extending that number, extrapolating it to more, do you think there will be further gains? Is it just a computational problem, or is there also some sweet spot in the middle?
I guess there should be some sweet spot, and maybe the 300 was their sweet spot in this problem, because the reason why we pick only one negative class to train the open set classifier is to let the model focus on running boundary between the positive classes and the nearest negative. And otherwise, the boundary will not be effective. That's our insight. So I think simply using all of the classes to train the negative boundary will not help much.
Great.
Thank you.
Thank you, Kuniaki, for answering the questions. That leads us to our second speaker, Chandramouli, who got the second place. And yes, I would like to remind you quickly that we have a hosted gather town that will start at the end of all presentations. And hopefully, if you have questions for the Haojin, whose presentation we just watched, you might have an opportunity to speak to them during that time. So without further ado, please. You are muted. Still muted.
Hello. Yeah, am I
Yes.
audible? Yes.
Yep.
Sorry. Yeah, I'd like to share my screen. So I'd like to present solution or solution to visual domain adaptation challenge. So I'll give a brief overview of what the challenge is, and then dive deep into the method, which I developed. So overview of the problem is most of the machine learning models today often fail to work on environments where it encounters out of distribution data, especially in real world cases. We have seen this happen where a model, uh, when it is trained on a certain distribution of data, and when it is put into work on a different distribution of data, even though the classes match, it doesn't tend to generalize better. So now what we tried is, instead of we tried to develop a solution where the model adapts to different target distributions classes on which the model was trained on. So we are focusing majorly on adapting the model to the target classes which the model has already been trained on. So here is a brief overview of the solution. So here we have training ImageNet 1K data, and so there are specific augmentations which I have used in order to make the model more generalized, and also the model architecture and different training techniques. On where I tried different training iterations, so I found the model uh, having best score that used all these training techniques. So based on the validation data, I was able to get the best accurate model and then submit it. So initially I'll talk about augmentations. So here basic idea of using cut mix and mix up is that real world data doesn't is not as close to what training data is. So in order to make it more difficult for the model to generalize, or like to make the model generalize better, I have used both cut mix and mix up. So where a portion of the image is cut and then it is replaced by another like image. So where the model is now trying to identify both the like categories of the image based on a single image, like multi-classification model. And then I've also tried to use mix up to like give more combinations of examples and their labels as well. So this is one part of the augmentations. I've also used horizontal and vertical flip, as well as like removing erasing, random erasing. So here I'm going to jump into the architecture of the neural network. So as today, most of the models have been working on attention-based architectures. So instead, I opted for an efficient net-based architecture, since it had it gave really good results on a classification-based task with an image resolution. I also tried to increase the image resolution to 600 into 600, because the efficient net perform both width, depth, and resolution-based scaling on its architecture, which I found gave much better results when compared to attention-based models, like some of the attention-based models like VIT and others. So I also tried to train two efficient net B6 models and then try to ensemble it on the data. But it seems that like single efficient net B7 outperformed the dual efficient net B6 ensemble. So we here use like, since I've also tried different image resolutions like 384, 400, and then 600 into 600. I found out that 600 into 600 gave better results because of the resolution, and as well as like the amount of information each pixel could give to the model. So here is the architecture of the model. And I have used Adam optimizer with LR is equal to 1 e power minus 4. So here are a few generalization techniques which seem to work, like especially when the model is training on multiple epochs. Exponential moving average help, because whenever there is a sudden change in the model weights across several epochs, EMA tried to like stabilize the model's weights instead of like having large oscillations in the weights of the model. So I've also tried to use drop block and drop out. So today, most of the models, in order to generalize, we use dropouts in a few linear networks and some of like in the linear layers. But I've also tried to use drop block as a generalization technique, because drop block, what it helped is, so instead of it tried to remove continuous patches of the feature space, so that model tries to like learn I mean tries to fit the data based on the features that is not available to the convolutional network or the linear layers. So drop block uh, made the model made help the model to generalize better, especially on the out of distribution data from where like on which the competition was held on. So, and also here is the loss functions which on which the model was trained. So the loss function here is focal loss, which tends to like, so focal loss in general tries to like uh, penalizes the model whose probability of class is less than 5, zero point 0.5. So whenever gamma is greater than or equal to 0, so when your probability of such class is less than 0.5, it tries to like penalize those particular outputs more when compared to higher confident classes. So this way, like it made the generalization of the model was much easier, especially because since we are trying to train it on data, like difficult data augmentations as well as drop block technique. The confidence was of the model was initially very low. I mean, output confidence. So using focal loss, uh, I mean, the model's confidence threshold was increased more than, I mean, gave it a boost beyond 0.5. So, and also this is one of the other technique I have used in order to introduce noise in the labels. So instead of having a single rigid label for the model to train on, I have like dispersed the model's labels into like into multiple categories, but having the most highest probability onto the model, I mean, onto the label, which was originally inside the data set. So this introduced noise in the labels, which accounts for any errors happening in the out of distribution data. So this helped the model. This also helped the model fit well on the out of distribution data, especially since my work, I'm focusing more on to like give better results on the classes which the model has been trained on. So yeah, that's uh, that's it from my end. So if there are any question and answers.
Yes, thank you for your presentation. Are there any questions from the audience?
I have a question, I guess.
Yeah.
Thank you for the presentation. My question is, so one part of the, maybe I missed this, but one part of the competition was giving in like a knowns or unknown
Yeah.
score. I was
Yeah.
curious what was used there. Was it
Like as I said, my work, I was more focusing on like fitting the model on the out of distribution data. So I hadn't like when I tried to use like when I tried training the model on out of distribution data, it did not work well in my case. So like out of the best solutions I had, this one was among them. So I submitted this to the challenge.
okay. Oh, thank you.
Okay, I also have one question.
Yeah.
About your training. So you introduce many kind of regularization techniques to make a model domain generalizable. Which techniques do you think was the most effective? Which technique improved the performance better than other techniques? Or you think all techniques?
I mean, I have a few in mind, like the data augmentation, especially cut mix and mix up gave a boost, especially in generalizing. Without those two techniques, there was a drop in the accuracy, like there was some like significant drop. And also I found out that drop block gave a real, I mean, a significant increase in the accuracy as well, because it was trying to remove continuous section of the feature space, right? So the model was trying to like fit into the data with whatever features it was available. Like even after removing the continuous section of the data, it was trying to fit in the data space. So that way, drop block also gave a significant increase in the accuracy. So,
I see. Yeah, that's interesting. Thank you.
Yeah.
Okay, in this case, if there aren't any other questions, I will remind the audience in case somebody came in that we will have a gather town after the end of all the talks where you can ask questions to, if you have any remaining questions to participants and to speakers that we will have shortly. Any additional questions that you have. And that leads us to Burhan. We are a little bit ahead of schedule, so Burhan, are you with us?
Can you hear me now? Oh, yeah.
Yep.
Awesome. I'll just share my screen and I guess I'll start. Um, can you guys see my screen?
Yep, you can see your screen.
Awesome. So my name is Burhan, and I'll be like presenting my work, pre-training transformers for domain adaptation, which was able to achieve like the first place at Visual Domain Adaptation Challenge this year. Current machine learning methods and models work really well in like constrained environments where the test data set is like really close to the training data set and has like the same attributes. However, like in real life applications, the input images might have different attributes than the one that are present like the constrained environments. For example, different orientation, like lighting condition, viewpoints, color scheme, etc., might hamper like the image recognition process. To solve this problem, various domain adaptation techniques have been proposed. Most of them belong to like the following two categories, which are moment alignment methods, which are designed with like classic metrics, which are such as trying to minimize the feature distance between like source and target data sets, max mean discrepancy, second order model, and some other distance metric based calculate or tar specific representation. GANs are pretty decent in like generation tasks, so hence adversarial learning is also be successfully explored in various tasks, including like domain adaptation. Several famous methods include ADDA, GVB, and MCD. However, these alignment constraints and strategies which involve are not specifically designed for like object classification tasks, such as like, I mean, if you try to like train your model, the optimization procedure of alignment from source to target or data set might be inconsistent to that of like object classification task itself, which could hurt like the learning discriminative object features for classification and thus result in like inferior object classification performance. Transformers such as like VIT, BIT, because of its like self-attention mechanism, seems to be like an obvious fit, but they require like big, huge chunk of data sets to train, and that's not an option. So if we go in like NLP realm, we see like one of the famous models is actually like BERT. That's like really efficient, effective, and it's like used in a lot of the real life applications. It uses like a mask language modeling MLM, which basically randomly masks some proportion of the token within the text, and then recovers like the mask token based on the transformer encoding results of like the corrupted text. If we try to like do something like BERT in like image classification scenario, then theoretically we can actually build a system that could like learn various attributes and cross apply it in like from source to target data sets. However, there are like few challenges. So the first challenge is actually like reconstruction process, because in BERT you're actually like feeding in like an input dictionary. However, in case of like vision or visual based systems, there's actually like no dictionary, so you can't use that. Moreover, I mean, if you consider this whole task as like a regression problem, which you're trying to like predict like the raw pixels, or you do it like a pixel by pixel approach, where you try to like predict like the raw pixel of the input mask inputs. You will realize that like, I mean, such pixel level recovery would like result in like wastage of modeling capacity, because it really focuses on like it's on a single pixel based values. And I mean, because of like high frequency details, I mean, it won't be able to like generalize, and it won't be able to like create like high abstraction based results. So to solve this problem, we are basically using BEIT, which is inspired from a BERT. So we take like an input image and resize into like 224 by 224 shape, and split that into like 16 by 16 patches, with each patch is of size of 14 by 14. Basically, it involves like the reshaping of input image into like AND patches. These patches like preserve raw pixels and are like use input features for the model. After like converting the image to like the patches, like almost 40% of the patches are like masked randomly via blockwise masking algorithm. Next, we actually need to like replace the mask passage with like a learning embedding vector. After which, like these patches are like flattened into like vectors and are like linearly projected, which is similar to like word embeddings in like BERT. However, a special token is also attached to like the input sequence. The standard 1D position embeddings are also attached to like patch embeddings, so that the position could be like retained of a particular patch. Simultaneously, an input image is also converted to like visual tokens via discrete variational autoencoder. This discrete variational autoencoder consists of an encoder and decoder. The encoder basically encodes the image to like visual tokens. I mean, the decoder's job is to like take the tokens and perform the reverse process. So each image is like tokenized into like grade of 14 by 14 visual tokens, and each grade size is like 8,192. We are actually like using a pre-trained tokenizer, I mean, as defined here in the reference. After like patches are like flattened, it is like fed to like the encoder. The encoder takes in like the input patches and produces like output vectors, which are like the encoder representation of like the image patches. The encoder representation are from the encoder are passed to like a mass image modeling head, which tries to like reconstruct the corrupted image patches by comparing it with like visual tokens obtained from discrete variational autoencoder above. For each mask position, we use like a softmax classifier to predict like a corresponding visual token. So the idea is actually to like maximize like likelihood of like correct visual tokens given like the corrupted input image patch, and minimize like the vision reconstruction loss. The whole idea is inspired by blockwise masking in BERT or its derived system, where it could be used for like various applications like next word or sentence prediction. The reason the images are cropped and patched rather than like pixel level information is like fed so that model doesn't like focus itself on like short range dependencies or like high frequency details, and focus more on like high abstraction. But since we are like patching the images into like blocks, the model is actually able to like retain high level abstraction information, which is like really necessary for domain adaptation task, since like the source and the target set actually belongs to like the same class in this scenario. However, they are like shift in certain attributes. One way of understanding the same technique is to assume this like whole model is actually a big autoencoder, which takes like an input image X. It's tokenized tokens, and also masked inputs. So what the model tries to do is actually tries to like make sure that like it is actually able to like successfully reconstruct like the patched image. So here like log like the highlighted region describes like the visual tokens based on like the masked image, where the Q such that Z is over X represent like the image tokenizer that obtain results from the visual token, and like the current highlighter region decodes like the original image given like the input token. So the whole pre-training objective is to like to minimize the log loss for visual reconstruction while simultaneously maximizing the correct token prediction based on like the given input images. After actually you have like pre-train the model, you can just attach like a simple classification head to the model, and then the model is actually like trained for like 500 more epochs with image size of like 224 by 224. It can also like, I mean, after some time you can actually like go ahead and like increase like the image resolution to like 384 by 384 while maintaining the same other parameters. So these are like the parameters that are actually like used. So simple color jittering, horizontal flipping, and random side cropping is actually used. We are just like using ImageNet for our experiments. So the first, our batch size like set to like 100. So for like pre-training, the whole model we're actually pre-training for like 500 epochs. Same is done for like fine tuning but for like the first 400 epochs, where like the image size actually like set to like the 224 by 224, like later for like the last 100 epochs is like such to like 384 by 384. There's actually like an increase in accuracy of like 1%. So that's cool. The architecture of like the encoder is actually like a VIT base model. It's a 12-layer transformer, 768 hidden size, and like 12 attention heads. So the data set that was given to us was like ImageNet. So for this experiment, we just used like ImageNet for like training purposes, even though we actually had like ImageNet CR ObjectNet for like tuning hyperparameters from source models. We in fact didn't use it at all. Since our model was actually able to like just learn the representations from like from the patch abstractions, we thought like it would be like a really good experiment where we can see whether this thing, if we can like further fine tune then down to like the same ImageNet data set, would the same model be actually able to like, you can say, work really fine on like the sets that's actually, even though they belong the same class, but that they're not part of it, like ObjectNet. So we're going to get to like the accuracy part later. Moreover, this model can also like auto separate objects and classes without labeling, because the whole pre-training task was like just dependent on trying to like reconstruct the tokens and basically learning based on that. So, however, we do believe that like pre-training this model with like hyperparameter optimizations based on like ObjectNet, ImageNet C, and ImageNet R will actually like increase the accuracy of the model. So in this visual domain adaptation challenge, our model ranked like the first place on the leaderboard. I think it has like the highest accuracy. But it's like area under curve was actually quite is low if compared to like the top 5 teams. The reason for that is like really clear here, because the models actually, like you can see, trying to like learn representations and attributes fed on like the input, but however it's not like a generalization model where it's like trying to like cluster like the representations from source to data, source to target. Our model was actually able to like surpass like the second place by 15% on just source only model, but our source only model was our adapted model, because we actually didn't create like an adapted model. So this clearly shows like this technique is actually capable of like picking up attributes from the source and can like link those attributes from source to target in like a completely self-supervised manner. These are like the results that are produced for like attention scores. I mean, I picked that from the paper from which actually like worked on. This is like done by a query key product in the last layer. For the each track layer reference point, we are used like the corresponding patch as a query and show which patch it attends to. After like retraining, the model is actually able to distinguish semantic regions via the self-attention heads without any task-specific supervision. This property partially indicates why this model is actually able to like work on downstream tasks such as image classification, or like further, if it goes further down, like semantic segmentation. So this actually improves the generalization ability of like fine-tuned models, especially on like small scale data sets. These are like further results down taken from like ObjectNet model, where like every output attention was actually added together to create this result. So you can actually clearly see like in these 3 images, like it's actually able to like perform like a really good attention to like the input features that's given. And so like the first image, there's like a floor with tiles. There's actually a wristband and like a weight machine. The second image is actually paying more attention to just a knife, and the third thing is just like some regions of like the bicycle. So since like semi-supervised self-attention mechanism can pick up like various attributes of the training data, it can also be like used for like variety of applications such as like object detection. So the future works that like I'm really interested in like working is like to make this thing work in like multi-attribute domain adaptations, where the source and target data set has like no correlation. So like that makes it like go in like unsupervised realm. I mean, also been like using this for like vision reconstruction in humans/animals via fMRI data, where I mean you just take like an fMRI and basically convert that to like a 1D signal and try to like regenerate what the person is actually seeing. So it's we actually have like achieved like good results, even though like that goes into like a different problem that the images are like not really clear. So we need to like work on that. And like I mean this thing could theoretically also like reach like open eclipse moment for like object detection, where you can actually just compare it with like just textual embeddings and try to like perform some kind of like cosine or dot product to like detect like objects. So that's like the end of the presentation. So if someone actually has like any questions, like they can ask me.
Great. Thank you very much. I actually have some questions. One question is, I did not quite get from the presentation, how did you end up generating the scores for that were used to compute the detection scores?
So I mean, what you do is like you just take like an input image, and once you convert that to like patch, and like you basically feed that to like BIT model. So the whole pre-training objective to like just take like a tokenizer from here, and like I mean for like every masked you can say patch, you try to like reconstruct it via like the visual token. So once you're actually able to like do that, and since like a random masking, and it is actually able to like learn like this, it pre-trains like the whole encoder. I mean that basically holds the information of like where to pay attention to for a particular object or scenarios. So I mean that could, since that could like also be thought of as like, I mean it's actually performing a high level abstraction for like various attributes. So once you actually like attach like classification head down like the realm here, somewhere here, and once you perform like the labeling or like supervised learning for a simple for like the pre-trained model, then it is actually able to like achieve the required results.
Right. So you're saying how you achieved accuracy, right? High accuracy.
Yeah.
So I was asking for the detection. So since there was also
yes, so I mean I was like thinking of like trying to like use some kind of like regional proportional RPN or something on like the head itself. So we are actually like taking like the RPN values and try to like you can say perform a dot product with like I mean, so you take like the whole region, I mean, then you can actually convert that to like a 1D vector of patches, and then you actually like perform like for like a single sentence, you actually like perform like a dot product from those like linearly embedding RPN embeddings and like your like textual embeddings. And then based on that, I mean, the best way I thought of was like try to like use some kind of like average or mean scoring function where you try to like make sure that like the mean loss is actually like really low. So then once you actually achieve that, then you can actually like use this to like perform or reach like the same moment where you actually like zero shot. So like let's say you train this on like a really big data set, like the encoder, then you can actually like zero shot that with like textual embeddings, and then it can actually like draw like a box for like every textual embeddings that you're feeding in.
I see. Another question, how did you generate the out of distribution scores? So there were two, like there was a prediction, right, generated, and there was an out of distribution score, like whether it's in domain or out of domain.
So I mean, I actually like for like this whole comparison, I was just like taking in like the in domain. I was like just like taking recording like the in domain, where like the source classes and like the target classes are actually belonging to like the same categories. Actually, and so that was like really high. But like I mean, if you compare that with like an out of distribution data set, actually like clustered that into like one category, which is like O. And it was actually able to like so that was like, I mean you could say 50, it was like 50 to 60% comparable, if I like remember that correctly, where it was like able to like do that for like most of this like the data set, but like not all of it. So there's that.
Okay, so did I get it correctly? You treated the out of domain label as just another class, like as
Oh
an
yes.
additional.
Oh yeah.
Got it. Perfect. That makes sense. Any other questions from the audience?
Yeah, I have a question regarding the I guess the tokenization.
Yeah.
So when you're doing the reconstruction and you're predicting the tokens,
yeah,
is this like a K-way classification? Because you have some set.
I mean, I'm actually like using DALI here. I mean, like one portion of DALI here, where I mean, I'm actually using a pre-trained tokenizer, so just get like the tokens in. But like, I mean, I've like later after this challenge, I also like tried to like create my own tokenizer. So like, some of the methods there, like where you try to like create like a source target attribute distribution tokenizer, actually like is actually able to like reach like comparable results.
I guess the question though is, so these are discrete tokens. So your VEIT model predicts some token. Is that trained with a cross entropy? I guess it is. Yes, you have to.
Yes, it is. It is. Yeah, it is.
So do you think you lose something because there's not like an ordering relation?
I mean, we are like taking the we are like taking like the ordering relationship. We are actually like feeding in like the positional embeddings for like our tokens. So I mean that basically ensures that like your input is actually like in the same way as like it's supposed to be. And yeah.
Thank you.
Okay. Thank you very much for your presentation, and thank you, the audience, for questions. I think we will make a brief break right now for around 8 minutes. So let's, or 7 minutes, like until, depending on your time zone, until, okay, let's say GMT. It is until 9:20 GMT. Okay, let's have a break. I'll put a splash screen. Hope to see you again in 7 minutes. Hello, everyone. Hope that everyone is back from the break. That leads us to the 3 remaining speaker presentations, 2 of them recorded and the last one live. Yeah, I will start just as a reminder, this is going to be recorded, so be careful with personal information if you share your screen.
And I'm assistant professor at UC Santa Cruz. Thanks for inviting me to speak at this VisDA-2021 challenge. Today, I'm going to talk about not all networks are born equal for robustness. Firstly, there's no doubt that deep learning transforms computer vision research. With deep learning, we can now have very excellent performance on some very complicated real-world image recognition tasks, like object detection and instance segmentation. And also with deep learning, we are able to generate very high fidelity images, and the human cannot even tell whether these images are true or fake. But meanwhile, there are a lot of works reporting that deep learning models lack robustness. For example, one very famous case is adversary examples, where people shows that by adding some small perturbations or print some adversarial patterns, the result images or the objects can consistently fool state-of-art computer vision models. Another case is about out-of-distribution samples. They show that when testing out of the box, including the scenarios that images with some weather conditions that not were covered in the training set, like the fog, rain, and snow, and also images with common corruptions, and the images with stylization to remove the texture patterns, but only return the shape pattern. In these scenarios, people find that deep networks generalize very poor here. So in this talk, I will introduce our works on improving network robustness. Specifically, we tackle this challenge from the perspective of designing robust neural architectures. The first work I want to talk here is feature denoising for improving adversarial robustness. So this is a pretty old work that we published in CP 2019, but I still want to talk about it because this is the first work that helps me establish the belief we indeed can have networks with better robustness. So in terms of adversarial images, if we just look at the pixel space, we cannot find any difference compared to their clean counterparts. But if we look at the feature space, here the feature space means the output from our intermediate layers of neural networks. If we look at these feature maps, we will find that our deep networks encode the clean examples and adversarial examples in a quite different way. More concretely, we can find that adversarial feature maps are much more noisy than the clean feature maps. So given this observation, our solution is pretty simple. We propose to denoise these feature maps to get better robustness. So to denoise these feature maps, we just consider some image denoising operations, but we put them at the intermediate layers of neural networks. So the image denoising operations that we consider are just some very traditional image denoisers like bilateral filter, median filter, mean filter, and the non-local means. One issue by directly applying these denoising operations is that they could lose signals. For example, if you just apply a median filter over your feature map, you will lose a lot of useful information. So to tackle this challenge, we introduce the denoising blocks. So basically, we add a residual connection to return the original signal. And here, another path is the denoising operation where we get the denoised signal. And we also have a one-by-one convolution here. So basically, this one serves as a weight to balance the trade-off between removing signals and returning the original signals. And with this denoising block design, we can just insert them at the intermediate of neural networks and train the host architectures in an end-to-end manner. So to train this network, we just apply adversarial training, which is invented by Ian Goodfellow in 2014. So the key idea here is that first we should get adversarial images, and then we just put these adversarial images to networks for updating parameters. So compared to the vanilla standard training, the only difference here is that rather than using clean images, we use adversarial images for training. Quite a simple idea. And we evaluate our models in the white box scenarios where the attacker knows everything about the models. So the x-axis is the attack duration. Basically, it indicates different attacker strengths. So more attack duration means you are applying a much harder adversarial attacker. And y-axis is basically just the top one accuracy on ImageNet. And this red curve is our baseline model. So it's the ResNet 152 plus adversarial training. And we can see that this evaluation curve become asymptotic. So empirically, that's a good news. That means we can have a worst case, a very reliable worst case performance in practice. And then we add the denoising blocks to this baseline model, which is shown in this yellow curve. We can see that by getting denoising blocks, we can get some very consistent and substantial robustness improvement over the baseline model. The next thing is that we evaluate our models in the black box setting. So here, the attacker basically knows nothing about our models. It can just only generate models in an offline manner and then send these images to our models for testing. So to facilitate our evaluation, we just attend our online competition where we need to submit our models for defending against 48 unknown attackers. And here is the results. So basically, our model ranked as the first place. We beat the second place by around 10%. And also, we noticed that starting from the third place, all models get lower than 10% performance. So it indicates that this challenge is an extremely non-trivial task. Lastly, we put some visualization here. So we can see that before the denoising operation, the feature maps are still quite noisy. But after the denoising operation, you can see much of the noise gets suppressed, and the response is more focused on the semantic and meaningful area. So this can qualitatively demonstrate that our proposed method indeed do some visual denoising for improving the robustness. The next work I want to talk here is smooth adversarial training. So for traditional deep neural networks, ReLU is the widely applied actuation function. For ReLU, first, it's pretty simple and easy to implement. And also, ReLU is quite efficient in terms of computation and memory. But if we take a closer look at ReLU, if first we look at the forward path, that's probably is okay. And the curve here is continuous. But if you look at the backward path, you can find that the gradient of ReLU take an abrupt change near the original points. So basically, the gradient suddenly change from 0 to 1. And this abrupt change, as we show in the paper, significantly weakens the robust learning. So one simple idea case here is that we first just change this ReLU to the sulfur plus. The sulfur plus is a very old actuation function, And in the forward pass, it's continuous, and in the backward pass, it's also continuous. So by doing such a simple modification, we surprisingly find that robustness can be boosted around 7%. And this observation can even generalize to other smooth activity function, which means by using functions that have continuous forward part and the continuous backward pass, we can always get better robustness. And this function basically include the CLU, GLU, ELU, and the smooth ReLU function. And here is the final results. We can see compared to the ReLU results, these smooth activity functions can at least improve 7% in terms of robustness. We also show their visualization of the loss landscape. We can see that compared to the ReLU function, if we use a CLU here, you can see the loss landscape here is much more smooth. Lastly, I want to talk about the robustness comparison between convolutional networks and vision transformers. So vision transformer basically is a very hot topic in the computer vision community. So here we just want to compare provide an in-depth and a fair comparison between these two types of models and see how they performs on different types of robustness. And this is basically our this year NeurIPS paper called Are Transformers More Robust Than CNNs? So firstly, to compare these two types of models, we need to select the specific instantiation of a convolutional network and the vision transformer. So here we select ResNet 50 as the instantiation of the CNNs and the DITS as the instantiation of vision transformer. Here the DITS is the first data efficient vision transformer that can successfully help enable transformer get a very good performance by training exclusively on ImageNet. The reason for choosing DITS can be detailed as the following two. The first is that they have quite a similar number of parameters. So it basically is a 25 million parameters versus 22 million parameters. And also by training these two type of models on ImageNet for 100 epochs, these two can get very similar top line accuracy. So we first look at the adversarial robustness. If we just directly test ResNet 50 and the DITS and evaluate against the PGD 100 adversarial attacker, we will find that DITS gets significantly better performance than ResNet 50. So for this result, we probably can say vision transformer wins this challenge. But if we take a closer look at the CNNs and the vision transformer, for CNNs, they by default use the ReLU function, while for vision transformer, they by default use the GLU function, which is a smooth one. So as we mentioned before, compared to ReLU, replace it with smooth exchange function can significantly boost adversarial robustness. So maybe the actuation function here is the key for improving adversarial robustness. So build upon our previous baseline, we additionally add our baseline, say ResNet 50 with GLU function. And we find that basically this model can get quite similar performance compared to the DITS. We additionally evaluated these models on the auto attack, which is a very popular parameter-free adversarial attack suite. We can find that these two models still perform quite similar. So based on these results, we can see that in terms of adversarial robustness, convolutional neural networks and the vision transformers are probably they're the same here. And next thing we take a look at is the robustness on out of distribution samples. So what we consider are three data sets. The first one is ImageNet data set So basically just benchmark model robustness against different image corruptions. And the second data set is ImageNet data set. So it's just a collection of some natural adversary examples. And the third data set is stylized ImageNet. So basically these images go through some stylization to remove their texture patterns and but returns their shape patterns. By evaluating ResNet 50 and DITS on this 3 out of distribution benchmarks, we can see that DITS significantly outperforms the ResNet 50. So basically for ImageNet, we can see the error rate reduced by 4.3. For ImageNet, we can see accuracy improved by 5.9. And for stylized ImageNet, we can see the accuracy improvement is 2.2. So maybe, so probably this result suggests that vision transformers are much more robust than ResNet 50 on out of distribution samples. To further validate this argument, we just do some training parameters of CNNs. For example, we align the actuation function between CNNs and transformers. We also align their ways to do the data augmentation. Additionally, we align some optimizers. But with all these experiments, we still find that vision transformers still outperforms CNNs on this out of distribution samples by tuning different training parameters. And next, we try a more aggressive way to align the training procedure of CNNs and transformers. So basically, we just apply the data, the knowledge distillation here. So we choose VITs as the teacher model and the CNNs as the student models. We want to use, say, through the knowledge distillation, can CNNs be as robust as transformers? And here is the results. Firstly, if we look at the ImageNet results, we can see that they get a pretty close performance, which demonstrates that the knowledge distillation here is successful. But if we look at this out of distribution benchmarks, we can see that ResNet 50 still perform much worse than the DITS. However, if we switch the role of vision transformer and CNNs, that means for teacher model, we set it as the convolution networks. And for student model, we set it as VIT. And here's the results. Firstly, with the ImageNet, they again perform quite similar, which demonstrates the knowledge distillation here is successful. And on the ImageNet, you can see that as a student model, it performs way better than ResNet 50. For example, on ImageNet, the improvements is 6.4. On ImageNet, the improvement is 6.5, and on stylized ImageNet, the improvement is 3.7. So this result probably demonstrates that the robustness, the robustness on this out of distribution samples probably is originated from the architectural design of vision transformer, rather than say by other training parameters. So to further confirm this, we introduced our hybrid model. So the hybrid model means here for convolutional networks, we additionally insert some transformer blocks. We can see that for this hybrid model, firstly, they can outperform the traditional CNN models on ImageNet and stylized ImageNet, which demonstrate that transformer blocks indeed is helpful for improving the robustness generalization. But compared to the pure transformer architecture, they still perform worse. So we can probably say this result can demonstrate that transformer block is the key for robustness generalization. And if you want to know more details, please come to our poster session which will be on December 9 from 8:30 a.m. to 10 a.m. So in this work, we basically introduce 3 works to improve network robustness. The first one is feature denoising, and the second one is smooth activation function. The third one is we find transformer blocks is the key for improving robustness generalization on out of distribution samples. So all this work can support that there indeed exist some neural architectures that are much more robust than others. So lastly, I want to thank my collaborators and also Facebook and OpenFair for supporting my research. I also want to put a small advertiser from my lab. So basically here we get, currently we have multiple positions for remote visiting students and a few PhD openings. So if you're interested in the works that I just mentioned in the talks, please feel free to send me an email. And thanks for listening.
Okay, this was one of our pre-recorded speaker presentations. Right now we are going to we're going to move to the next presentation in our schedule, and then we'll have the presentation on intelligence and deep learning, and after that we'll have a gather town that, as I mentioned multiple times, some of the speakers that gave recorded presentations will still visit, and therefore you can ask them some questions that you might have there. Okay, without further ado,
Hello, I'm Saining from Meta AI Research Lab. In today's workshop, I'm going to talk about model robustness from the lens of natural image corruptions, data augmentations, and representation learning. In this talk, I'll mainly cover 2 directions. In the first part, I'll be talking about our NeurIPS paper on the interaction between corruptions and data augmentations for natural corruption robustness, where we introduce a new benchmark dataset called ImageNet bar that reveals some of the caveats in measuring the corruption robustness. In the second part of the talk, I'll be talking about a new self-supervised learning approach, masked autoencoder, recently developed in our group. And exclusively to this workshop, I'll be sharing some of the robustness results for our model. Okay, so I'll first introduce our NeurIPS paper on interaction between augmentations and corruptions in natural corruption robustness. This is a joint work with Eric Minton, Alex Krylov from FAIR. This paper will also be presented later today in the poster session. Among many different robustness challenges and tasks, robustness to common image corruptions is a particularly interesting and important problem. As shown in NeurIPS 18 paper, humans usually have no problem in recognizing objects, even when the images have been severely distorted. But some of the deep learning models face challenges. From practitioners' perspective, corruption robustness is also important for real-world applications. For example, the distribution shift between test and trained images due to the corruptions can be very common. Additionally, adversaries might come up with distortions that evade an AI-based detection system. Then introduced the CIFAR10C and ImageNet in their iClear 2019 paper, which has become the widely used benchmarks for researchers to test the robustness of their models in a quantitative way. To recap, ImageNet is a collection of 15 natural corruptions, shown on the right. Those include pixel noise, different blur patterns, weather effects, and also digital effects. One thing that is so obvious and so important is that the corruptions should be unknown at the training time. Otherwise, a trivial solution to the benchmark is just using the corruptions as data augmentation during training, then there will not be any domain generalization problem, and you'll get like really good numbers, but this is not what we want. On the other hand, many recent papers show that training time augmentation often improves corruption robustness. For example, auto-augment, augmates, patch Gaussian are some of the data augmentation techniques that argue to offer better robustness. To avoid the trivial adaptation, people usually manually remove any augmentations that overlap directly with the corruption benchmark you are measuring on. In our work, we try to answer the following question. Is this really sufficient to simply just remove the exact overlapping augmentations? To motivate this, we show a simple toy example here that might suggest that the answer is no. We test the model on one corruption category, in our case, motion blur, showing on the y-axis. And we train the model with different data augmentations listed on the x-axis. It is expected that if we train directly with motion blur as data augmentation during training time, we achieve the lowest corruption error. But you can also see that some geometric transformations, such as translate and shear, also yields significantly better corruption robustness. And they are almost similar to the performance of directly training on motion blur. While you can also see some other augmentations, such as color augmentation, do not help corruption error for motion blur at all. From this example, we can see that visually similar but not identical augmentations can significantly improve the model robustness on given corruption. This motivates us to do the following. First, we need a way to quantify the similarity for image transforms in order to measure the distance between a data augmentation and a corruption. Then, we would like to show that this augmentation corruption similarity can predict corruption error and is oftentimes the confounding factor in robustness improving schemes. Finally, if our hypothesis is correct, we would like to verify that several augmentation-based algorithms will have worse error on corruptions dissimilar from ImageNet. First, we'll be talking about how we quantify similarity for not image contents, but for image transforms. Ideally, our transform similarity measurements should meet the following requirement. First, the similarity should be able to capture the perceptual distance. If two similar transforms are applied to one single image, the transformed images should look visually similar to human. And second, as we just said, the transform similarity is about measuring similarity between two image transforms, not the transformed images. To do this, we'll try a very simple but effective method that was inspired by the perceptual similarity work commonly used, for example, for style transfer. The idea is to extract the features from a trained network and use the feature distance as a proxy. Here we train two residual networks without any data augmentation, and we extract the features from late layers to compute the L2 distance between two transformed images. So to marginalize the image contents and make the comparison about the transforms themselves, we simply average over the subset of dataset. So here, Ft defines the feature space for a given transform T, where two perceptually similar transforms should be closer. The second issue we're trying to address is that we really want is to compare an augmentation distribution to a corruption distribution, rather than just the individual augmentation and corruption. A standard distribution comparison, such as MMD, is not sufficient, since the distance between augmentation distribution and corruption distribution can be really big, even when the augmentation can produce samples close to the corruption. Here we introduce the minimal sample distance measure. We will compare the center of the corruption distribution to the closest sample drawn from a large number of samples from the augmentation distribution. This will make sure that as long as the augmentations covers the corruption distribution, the distance will be small. On the right, we'll provide a quick toy example to show that minimal sample distance is practically more useful to characterize the distance between augmentations and corruptions. Details can be found in our paper. Now we have a measure for augmentation corruption similarity. We want to show that this is indeed a predictor for corruption error. So to establish the correlation, we would like to generate a large number of augmentations. To do so, we adopt the idea of Augmix, which provides 9 base transforms. And we keep all subsets of those base transforms, and then we can get 2 to the 9 or 512 composite augmentation schemes. So for each augmentation scheme, we'll train a wide ResNet on CIFAR10 and evaluate the corruption errors on CIFAR10C. At the same time, we'll also measure minimal sample distance to each corruption in CIFAR10C. So now we have 2 things, the corruption error for each of the augmentation scheme, as well as the transform similarity between transformations and corruptions. We can then plot the similarity error correlation plot, where the y-axis is the corruption error, and the x-axis is our similarity measure. So each dot in this plot is an augmentation scheme, either coming from the 512 Augmix power set, or the real augmentation scheme from literature, such as AutoAugment, Gaussian, and Augmix. We observe that there is a generally strong correlation between similarity and corruption error, and the Spearman correlation coefficients are quite high, except for several corruptions, such as brightness, where the correlation is pretty low. Now we established that the perceptual similarity between augmentation and corruptions are good predictors for corruption error. We want to argue that this is actually matter for evaluating augmentation-based algorithms on corruption benchmarks like ImageNet. To do so, we collected 30 new natural corruptions similar to the construction and collection process of ImageNet. We then constructed a dataset of 10 corruptions with the same baseline difficulty as ImageNet, which means like for model trained with augmentations, the corruption errors are at the same level for both datasets. So the new dataset is not simpler or harder in nature. We then use our similarity measure to find the corruptions that are most dissimilar from ImageNet. We then benchmark the augmentation schemes from the literature on this new set of corruptions. So the idea is that if an algorithm generalizes well across very different and unseen corruptions, the corruption error on this new dataset should be similar to it on ImageNet. But if the robustness gain is coming from an overfitting behavior due to the overlapping augmentations to ImageNet benchmark, then we can expect a big performance degradation for corruption error in the new dataset. So this is an illustration of the 30 corruptions we generated. We can see that they are pretty reasonable image distortions that are similar in spirit to the patterns of existing corruption robustness benchmarks. For example, we have different color distortions, geometric transforms, blurs, and pixel noises. So after the dissimilar selection procedure, we end up with 10 corruptions, each for both CIFAR and ImageNet datasets. They will call them CIFAR10 C bar and ImageNet C bar, which suggests the dissimilar nature to the original ImageNet and CIFAR C datasets. The table below shows the results of many robustness aiding data augmentation schemes in the literature on ImageNet C bar and CFAR C bar. And the third column, you can see the performance difference between the two. Even though the baseline numbers are almost identical, every single data augmentation schemes perform worse, sometimes by a very big margin that actually changes their ranking. This shows that when benchmarking different augmentation schemes, we need to be very careful to make sure that improvement is actually real. On the positive side, we can see that even those data augmentation schemes degrade on ImageNet C bar, they are still performing better than the baseline, which means that there are some degree of generalization to unseen corruptions, but we just need to be cautious when we're evaluating them on a single benchmark. So in conclusion, we show that augmentation corruption perception similarity is a good predictor for corruption error. This suggests that just removing identical corruptions from data augmentation may be insufficient, and to make robust progress in corruption robustness, we need to be very careful, especially when we are drawing conclusions based on only one benchmark dataset for evaluation. On the positive side, we have evidence that strong data augmentation can offer improved robustness to even unseen corruptions. It's always a good idea to test on complementary benchmark, such as ImageNet C bar, to reduce the risk of overfitting. In the second part of this talk, I'll quickly introduce our recent work on masked autoencoder, a new self-supervised learning algorithm, and its implications in model robustness research. Recently, advances in NLP are mostly powered by the large-scale training with larger models and bigger datasets. The simple algorithms, such as BERT or GPT, that can scale efficiently marks the new era for NLP research and led to many new applications and provided sustainable improvement across tasks. In computer vision, self-supervised pre-training, despite achieving pretty good progress in recent years, still lags behind compared to what happened in the NLP community. In terms of the self-supervised learning paradigms, contrastive learning methods such as MoCo or SameClear have been the most successful ones. However, there's little signal that those methods can actually scale to a bigger regime. One possible reason is that contrastive learning frameworks focus only on learning invariant representations to the underlying imposed data augmentations. In our recent work, we move away from the contrastive learning framework and explore a BERT-like algorithm that we call masked autoencoders, or MAE. The idea of masked autoencoder is very simple. Given an image, we randomly mask out the image with a substantial ratio, such as 80%. The encoder sees only the remaining 20% image contents and output the feature embeddings. After that, we add the mask tokens to the sparsely sampled sequence, so we will have the full-length sequence for the subsequent decoder network. The decoder is a very small transformer network that decodes the sequence and reconstructs the masked patches. Then we'll just compute the L2 loss between the input and output. The entire algorithm is an extremely simple autoencoder network. Here is an example of the masking and reconstruction. So 80% of image patches are masked out, and the network is going to reconstruct the image based on the remaining 20%. It is not an easy job even for humans. As you can see, the reconstructed samples are indeed very reasonable. Compared to the ground truth, there are some missing details, but overall the bus was reconstructed very well, using only the 20% of the image. Here is another example. For a full set of examples, please refer to our paper. So MAE achieves new state-of-the-art results on image at 1K clean accuracy without using external data. But what's most exciting is the scaling behavior it exhibits. Original supervised training of VIT models faces challenges of severe overfitting, but with MAE pre-training, there's stable and consistent improvement moving from the base model to large model and to huge model. A scaling behavior of self-supervised MAE is also similar to the behavior of supervised pre-training paradigm using large annotated datasets such as JFT. The representation can be transferred to downstream tasks and bring very significant gains across different tasks, and larger model often leads to bigger gain in performance compared to the training from scratch baselines. For the audience in this workshop, one thing that might be interesting is the robustness or domain generalization behavior of the MAE pre-trained models. Does the good scaling behavior also apply to the various of robustness benchmarks? Here I run the experiments for our MAE pre-trained VIT models and evaluate the performance on 7 different robustness benchmarks, including FGSM, PGD attack, and ImageNet-C and ImageNet-C bar, as well as ImageNet-A, renditions, and also sketch. So we compare the results with standard models such as DEIT and swing transformers, as well as transformer models designed specially for the robustness purpose, such as RVT. Here are some interesting observations. At a relatively small model regime of VIT base, MAE pre-training helps on ImageNet-A, rendition, and sketch, but leads to worse performance on FGSM and PGD, as well as the corruption robustness. It will be very interesting to study if this behavior is related to the MAE training strategy. When moving to bigger models, similar to the clinic case, MAE shows amazing scaling behavior across the board. With a VIT huge model, we can easily achieve state-of-the-art methods across all the robustness benchmarks, for example, getting 33.8 ImageNet-C corruption error and 64.4 accuracy for ImageNet-R. It is not very surprising that bigger models can lead to better corruption results, but I think there are several interesting questions to think about. For example, for network robustness research, the experiments are usually done with small-scale models. Will the innovations still matter for large computer regime? How can we verify that without training the huge models, which can be invisible to many? Cihang just presented some really cool research on robustness behavior across network architectures. It will also be interesting to study the robustness behavior across different training paradigms. For example, training from scratch, supervised pre-training, and different self-supervised pre-training schemes. Finally, representation learning in computer vision is largely driven by ImageNet 1K dataset still. So far, from the network robustness perspective, it looks like this might be okay. Strong models on ImageNet 1K are also very robust ones. Where is the breaking point? What does it mean for robustness research when we move towards large-scale uncurated data for representation learning? This will be a very interesting direction to study. I don't have answers for those questions, but I can see that things are quite different now entering the decade of 2020s. I call it the post-VIT era, since in computer vision history, there's no time like right now that we care so much about model scaling and large-scale training. It might be the time for us all to embrace the big models in computer vision, and robustness research will be even more important to make sure we are on the right track. That's all, and thank you very much.
Okay, this leads us to the final presentation from our speakers, from Zhongqi Miao. He's a PhD student at the University of California, working with Professor Stella Yu, Professor Bing Gates, and his research focuses on computer vision and deep learning applications to ecological datasets and the problems emerging from these applications, such as long-tail distributions, multi-domain adaptation, and active learning.
Yeah, thank you very much for your introduction. Let me share my screen. Can you see my screen? Okay. Hello, everyone. My name is Zhongqi Miao. I'm a 50-year PhD student from UC Berkeley, working with Professor Stella Yu and Professor Wayne Getz. Today, I'm going to talk about challenges of deep learning during the applications to real-world ecological datasets. So start from a case study. Basically, the case study is about wildlife imagery monitoring in a place of Serengeti in Africa. So basically, the idea is that people put like cameras, automatic cameras in the wild and automatically collect wildlife imagery from those cameras and use those collected data to monitor the animal population dynamics and the community changes with respect to human intervention and climate change. So basically, these are the examples of those cameras and the images that are collected by those cameras. And people need to manually sort or classify those collected cameras to get the sense of how the data are changing over time. So the problem is, for each year, the site that we're having, which is a relatively small site that has like about 80 cameras, it produces like over 3 million images every year. And basically, it will take like about 500 working hours for maybe like 2 wildlife experts to go over every single of those images, such that it is possible for them to do like further analysis. And it's extremely expensive in terms of time. And so people are actively looking for good automated methods that can help them to automatically classify animal species from those automatically collected images. And from the year 2007, deep learning was introduced to the ecological community, telling people that it is possible to use the state-of-the-art methods to automatically identify images from those, identify different kind of animals from those images collected in the wild, and saying that the performance is pretty high and the speed is going to be extremely faster compared to manual classification. Then after that, I was one of the people that trying to apply deep learning into those wildlife classification area. But the problem is, after I have started the applications, some unexpected challenges emerges. So the very first one is like introduced by, like what it was introduced was the distribution of long tail. So basically, naturally collected data are like having a natural distribution of animals. So basically, animals are not balanced distributed in the wild. There are abundant species and there are like a lot of rare species. So those kind of distribution definitely will cause performance imbalance with respect to the distribution of the data if we directly apply recognition models, like plane recognition models on those types of data sets. That's the very first challenge that we have encountered by applying deep learning into our data sets. The second one is, so if we don't want to deal with like those imbalanced distribution and only focusing ourselves on those balanced parts of the data, for example, the head classes or the abundant classes usually perform pretty well. If we only focus ourselves on those classes as a starting point, and usually we will get like a relatively better results compared to the overall data sets. But the problem is, after we have trained the model using those abundant classes, and when we want to use the model to inference newly collected data, usually it can come from like different seasons or different study sites that have like different backgrounds. There can be like domain problems, especially like discrepancies in the backgrounds or the environment. If we don't do anything, then the model is going to have problems on like recognizing anything from the newly collected data. And if it is only like a seasonal changes where it's only like a background change, and we know which season is going to come, which make it as like a single target domain adaptation problem, then it is pretty easy to just adapt the trained model from one source domain to one single target domain. Then that's not going to be a problem. But the problem is we never know how many possible domains that we will be encountered in the future. So that's the biggest problem. If we know the exact number of possible like target domains, we always will have like ways to adapt our model to like a multi-target domains in the future. But the problem is we never know how many targets that we will be seeing in the future. And the same thing also like happens in like a traditional domain adaptation problems, especially like self-driving. For example, if we train our model on one single like weather conditions, and then we put the car into like the open world driving conditions, all sorts of like weather conditions can happen, and all sorts of like road conditions can happen. It is never possible for us to like define a specific number of target domains. But domain adaptation is not always the biggest problem, because within like the traditional definition of domain adaptation, we always know like the source domain and the target domain have like the same numbers of categories, like the numbers of categories are fixed. But in reality, especially for like ecological data sets, when the projects expand themselves, like people are setting up like new cameras in different sites, like people are trying to monitor different areas of the world, it is always possible to like have a continuous change in the target categories of data set that we're having. We can have like a more different new categories that's never seen before in previous model or in previous data in previous study sites. And there can be like animals that got that are extinction. So basically the numbers of categories are changing over time. And traditional domain adaptation method is not going to be helping us to identify like novel classes in this case. And we will always like rely on human annotations to tell us what's actually being collected as like novel classes. So all in all, those human annotations is always inevitable if we want to keep our model work in the future all the time. So in that case, that goes to like the three major challenges that we have encountered during our applications of deep learning in like a real world ecological data sets. And what we are thinking is that the most interesting and important challenge here is humans in the loop, because we're thinking if we can actually utilize humans in the loop more in the most efficient way, then both long tail problem or multi-domain problem can be relatively relieved at the same time, rather than like just focusing on one of them at one time and like having really complicated model to solve one of the problem, and then it doesn't work for other types of challenges at the same time. So there goes to one of our most recent projects about continuous domain shift with humans in loop. The title is like iterative wildlife recognition framework. So if we take a closer look at this representation over time, so it's not simply trying to say that the number of categories keeps growing over time, such that we need to like being continuously able to recognize novel samples over time. At the same time, it also shows that the distribution of the collected data is changing over time. So instead of like only having novel class, we would also have like data that collected from different environments, having different having discrepancies in the appearances, or like for example, for the same species, but they have like different types of attributes. For example, the same types of carnivores living in Africa or living in Asia, they usually have different appearances on their body, or markers. They call it like a subspecies. But ultimately, usually people just don't want to do like subspecies classification. They just want to know whether it is a tiger or a panther. But panthers in Asia or panthers in Africa usually might have like different types of body marks. So they can have like a lot of types of distribution shifts over time. So in this case, this illustration basically is telling us that if we want the model works in the future, then we need to deal with a continuous distribution shift. And how to deal with that with human in the loop incorporated. So by simplifying this illustration, basically we're thinking it is a loop. So it is a loop of data collection and human annotation and AI model training. So what it means is that during time, we will be continuously collecting new data. And if we want to make sure whether there are novel species or novel classes incorporated in those newly collected data, we need to have some human annotations to tell us whether there are actually like novel classes. And then we use those newly annotated like the data to update our model such that the model is more generalized and more powerful. But the problem is, if we use human annotation on every single image or every single data that we collected in the future, then there's no need to have AI models anymore, because we're using human annotation on every data anyway. So why would we still want to like train our model? It's not going to do anything. So we're thinking maybe if human annotation is inevitable, then whether it is possible to make those human annotation as small or as limited as possible, such that we don't want to use human annotation or human effort on every single data that we collected from the future, and such that we are using human annotation in an efficient way, and AI models can actually help us to get a more efficient human annotation in the future. So that's our intuition, whether it is possible to incorporate human annotation and use the help of AI models such that the loop is closed and every single component in the loop is necessary, instead of like, or if we want to use human annotation on every single data, then this green arrow probably is not that necessary anymore. So in that case, we proposed a framework with time component incorporated or considered, where for each time step, it is we have collected, like for example, new data, and then it goes through our previously trained model, and then the model tells us using a confidence prediction, confidence metric to tell us how confident the prediction it is. And then for high confident predictions, we treat it as like a pseudo labels or trusted predictions. And for low confident predictions, we go through human efforts or human annotations. So basically, the idea is that we only want to use human effort on those lower confident predictions, and then we want to trust the predictions that has high confidence. And then in order to update our model, we use the high confident predictions as pseudo labels, and along with the newly acquired human annotations to update our model such that it is more generalized and more powerful in the future, and it has like the capacity to identify those novel classes or those hard classes. The problem, so this, you can see this framework is like developed upon the idea of active learning and and semi-supervised learning. But what's more important is here the idea of low confidence prediction. It's not simple OOD. So for OOD problems, people simply want to do one single task. It's like distribution and auto distribution. But in this case, we're not only focusing on inner distribution or distinguishing between inner distribution and outer distribution. At the same time, we want the model to say the lower confidence predictions or those samples that causing troubles. These samples can not only coming from new species, it can come from like tail classes. Because it's from tail classes, then the model is not going to have like higher confidence. And then it can also be samples from different domains. So it can have like a different attributes or different, I mean, not attributes, different like appearances, backgrounds, or other noises. So because we think like the most basic way of doing domain adaptation, especially for samples from different domains, is like fine-tuning them. But because domain adaptation was set up like we don't want to do annotations, so we want to adapt our model to those like additional domains. But in this way, it is possible for our model to like figure out automatically or actively choose some samples that it cannot handle, then give human annotations to those samples, and then do fine-tuning, like just directly transfer learning. It is making this overall idea relatively simpler and making it working in terms of like future applications. And if the coming data, I mean, a large amount of the coming data is coming from like the same domain, then we probably don't need to do like a large portion of domain adaptation, and then we can limit our human annotation to a very small portion of the newly collected data. If a large amount of them are coming from a new domain, then hopefully it will have like a low confidence on almost all, a large amount of, a large portion of the newly collected data, and then human efforts will be like required more on those newly collected data. So we can see that the amount of human effort is relatively dynamic. If the data is pretty hard, then we need more human annotations. If the data is pretty easy, then we need relatively less human annotations. And in order to like do experiments with those types of framework, we like designed a small experiment loop where we only have like two time steps. In the first time step, which we are just basically training a backbone or off-the-shelf recognition model. It can be like either resident or any types of recognition model. Then in the second time step, we have like a new data coming in, and we hope the model can do the confidence like active selection, and then do the semi-supervision to update the previously trained model from T0. And this is basically the workflow of the overall thing. So in the first period, we train our model, and then we have a classifier. Then this classifier is used to inference new data collected from the second period. And if it has like a high confidence, then we use like pseudo labels. It has like a low confidence, we use like a human annotations. And for the results, relatively, we do not want to focus ourselves on like a pure classification accuracy, but also we want to know whether the model is able to sort out a lot of like novel samples, and whether it can have like a high confidence on the in-novel or known species or the known classes. So here we can see it is possible to do that. For example, it is having 78% of confidence ratio on the inner distribution and 75 of unconfident ratio on the novel samples. And then for the confident predictions, it has like over 92% of accuracy, which means as long as it is confident, the accuracy is pretty high. And then in this case, we're saving almost like a 20% of human annotation or human effort, because 78% of the data were considered confident. And it's the same for the novel classes. And finally, the idea is that we're saving a large amount of human effort, but we're not totally eliminating that human effort, because we know that it is not going to be possible in the near future to have a 90% accuracy performing model all in one without any human intervention. So we're basically finding a method or a way to like helping relieving the amount of required human effort. At the same time, it is sensitive to novel classes, such that a large amount of novel classes were identified and feed for like a human annotations. So basically, that's the idea. And at the same time, we're only proposing this overall framework, but we're not proposing or suggesting what kind of method is the optimal method. So every component in this framework can be changed with better method in the future. Like we can have like a better recognition model such that it has like a better recognition performance in the first place. And it has like it can have like a better uncertainty metric that involved and gives us like a more sensitive, higher and lower confidence separation. And it can replace with those like a semi-supervised learning with better methods to update the model. So basically, the idea is that we only want to propose or promoting this overall data collection and active selection framework instead of like one single component. And the good thing is that this overall framework is already like applied in the field, where field ecologists are feeling fine, where the model is not working perfectly well, but it's telling them which part of the data is working well and which part of the data is not, such that they can trust those data that were working well and spare some effort of annotation on those data that didn't work well. And to them, almost like 80% or 70% like human effort relief is already a huge relief to them. They are not looking for like 100% effort relief in the first place. So 70% for them is already a good enough number, rather than like some model that can automatically give them like 100% accuracy, which is pretty hard to do. And then besides that, if we go back to the distribution shift, so because the distribution shift is not always limited to like fixed categories, we will always be require some like a human effort to give us annotations for the novel classes. So it goes to an interesting like idea or interaction between humans and the machines. So in that case, because machine learning is not going to automatically tell us like what types of novel classes it is. The best it can do is just OOD detection. So the model itself is not going to be like a perfect. And then human by themselves or human effort by themselves are not efficient at all either. So by involving those two parts together, then the overall framework is more organic than before, than like totally eliminating human beings or totally eliminating like the effort of machine learning. So besides this overall distribution shift framework, we're also like thinking a more organic relationship between like humans and machines, where machines is not always going to be perfect and the humans are not efficient, but together they can have a like really working types of relationship or framework that can like that doesn't matter whether the distribution of the coming data is changing. This organic framework can actually adapt to all sorts of distribution changes in the future. So basically, that's what we are having for this specific project. And here is the project page of that paper. Yeah. Thank you very much. and I'm happy to take any questions.
Thank you. Are there any questions from the audience?
Hi, just a single question. I mean, great presentation. Let's say like, I mean, a new class that's not actually like trained or pre-trained on the model is like fed in. So like, how's like that model, like, how's like the model getting updated from like those human annotations because like it doesn't contain that particular class, right? Is it using some kind of like incremental learning or some kind of like feature clustering or distillation techniques or something?
Oh, so basically two things. The first thing, those models are trained from previous data, so it already has a classifier. And sometimes the classifier is not going to work on the new data because the new data has like novel classes, right? So the first task for the model is to have like predictions on the newly collected data with a confident metric along with those predictions. And hopefully the ideal case is that the model is able to do a perfect OOD, out of the distribution detection, such that all the novel classes were separate out, and those novel classes were provided human annotations, such that we would have like a new annotations on novel classes. At the same time, for the inner distribution, it is possible for the ideal case is that every single inner distribution data will have like high confident predictions, and we will going to be we will trust those predictions and use those predictions as pseudo labels. So in order to update the model, we use those pseudo labels along with human annotations for the outer distribution to update the model such that it is more generalized to either identifying in the distribution data because basically we're having more data. And at the same time, it is also possible to identify novel classes because we are providing annotations on those novel classes. So basically that's the most ideal case of this framework. So basically the first thing it does, all the model are pre-trained. So pre-trained by the previous time steps. So every single time step is a training and updating process of the model. And in the future, the model is already considered pre-trained. The second thing is that because we have like a training process, so the classifier itself already have like a classification capacity. So it does not have any like, it does not need to do a lot of like unsupervised either attribute clustering or things like that, because what the classifier needs to do is basically first predict, make predictions on the newly collected data. Second, give us like prediction confidence along with those predictions such that we know which predictions are confident and which ones are not, and then go to the second and third steps. Does that make sense?
Oh, yes.
Okay. I have some more questions, but maybe we should shift towards them to the Zoom, to the Gather Town room, if you do not mind. We have some
sure.
time. So in order to this wraps up the live part of this break session. Thank you very much everyone for coming. The recording will be released at some point in the future. Hope to see you next year, and let's all go to the Gather Town now. The link can be found on the website. Let me share my screen to show where.
So, I can also share it here in the chat.
Oh yeah.
That also works. So there is this Gather Town, and there is a password that I'll also post into the. Yep, that is also in the chat. So for further questions, hopefully some of the speakers will also join us in the Gather Town. The ones that weren't available for the Q&A. Thank you everyone very much for coming, and Thank you, four speakers, for presenting and answering our questions. Hope to see you next year. Please join our mailing list if you haven't yet to receive notifications about future challenges. Thank you.